So for the first question of Review Quiz Chapter 8, we have a simple random sample of size n equal 81 is obtained from a population of mu 80 and sigma 18. So describe the sampling distribution. Well, if it's a simple random sample taken from the sampling distribution or from the population, then the sampling distribution, because n is greater than 30. Yeah, 30. Because it's over that, we can assume it's approximately normal. It wouldn't be uniform. There's no reason to assume it's uniform, skewed right or left. There's no way we could tell based on the information, and the shape of the distribution is unknown. Really, it'd be that one, but because it's a simple random sample from a large population, n greater than 30, we can assume it's approximately normal. That's nice because now we can look at the rest of this using the sampling distribution formulas that are given. The first one, of course, is the mean of a sampling distribution is always going to be the same as the mean of the population. So here we had a mean of 80. So we're going to have a sampling mean of 80. Now the standard error of the distribution here, that's going to come from the formula. I believe it is the standard deviation from the population divided by the square root of the square root of the sample size. So that's the standard, standard error of the mean for the sampling distribution. Let's go back. So if we pull up a calculator, okay, let's look at the standard deviation is 18, and then divide that by the square root of the sample size, which of course is 81, so square root, that's going to be 9. 18 divided by 9 is going to be 2. So the standard error is 2. And now, since it's approximately normal, we have a mean and a standard deviation. Well, that's a good place for StatCrunch, because now we can create the normal distribution. If you go to Stat, Calculator, Normal, that gives us the calculator for the standard normal curve. But of course, we're going to be changing the mean and standard deviation. So mean is 80, standard deviation is 2. And we're looking for what is x greater than 83.4. Compute that. Area under the curve is 0.0446. 0.0446. Okay. The next one says x less than or equal to 75.1. Compute that. We get 0.0071. 71. And the last one is the in between. So between 77.1, 84.4. Okay, looks like we got 0.9127. 9126. 9126. Let's check that. And we're all good to go there. Okay, this problem's very similar. A simple random sample of size n equal to 39 is obtained from a population with a mean of 68 and a standard deviation of 18. What must be true regarding the distribution of the population in order to use the normal model? And then assume it's true, what do we have? So the only thing, the population can be left, right, or normal distributed, or it could even be uniform, it can be whatever. But all we really need is the sample size to be large enough. As long as n is greater than or I think equal to 30, then the sampling distribution will always be approximately normal. So that's what we need. We don't need the population to be normally distributed. We don't need it normally distributed, and we, of course, we would never must be assumed to be normal. We are assuming it's normal because of the fact that the sample size is large enough. So that one obviously can't be. So got to be B for that one. And then using the normal model, of course, you see the mean is 68. That's because it's the same as the population mean, which you'd expect. And we know that the formula is the standard deviation, 18, divided by the square root of the sample size. 18 divided by the square root of 39. That is part C. Now, we can open up StatCrunch, use the normal distribution to calculate all those probabilities there for us, like we've been doing. First, I should actually see what is the approximation to the standard deviation, or the standard error, I should say. Okay, we got 2.882307. 882307. 882307. Okay, the mean is 68. First one is x less than 71.5. Compute that. 0.8877. Okay. Greater than 69.8. Compute that. We get 0.2661. All right, let's check those answers. And we are all correct there. Moving on. Okay, for this one, we got just kind of a word problem about pregnancies of animals and their lengths. So the days, we got 191 days for the mean and 16 days for the standard deviation. All these look to be just questions on that, but the first one's not on the sampling distribution, and I think the rest of them are. So this first one says, what is the probability that a randomly selected pregnancy lasts less than 185 days? So this is just straight from the population, or yeah, the population mean and standard deviation that are given there. So we can, it says here, they are approximately normally distributed. So let's just use the normal distribution calculator. Yeah, make it look a little bit better here. All right, that's better. And we have a mean of 191, standard deviation of 16, and we're asking lasts less than 185 days. Compute that. 0.3, let's see, 4 places, so 3538. Right? Interpret this probability. So if 100 pregnant individuals, well, I should say 100 pregnant animals were selected independently from this population, we would expect blank pregnancies to last more than, no, it wouldn't be last more than, it's a last less than. So definitely less than, not exactly 2 either. So it's going to be B. And we would expect it to last, well, we move it 2 places past, we get 35.38. Rounded is just 35. So that's the interpretation of that. Now we are looking at a random sample of 20 pregnancies. And now we can look at the sampling distribution versus the population distribution. So the sampling distribution of X is normal because the population is approximately normal. The sampling will definitely have to be normal. Okay, the mean is going to be the same, 191. And the standard error is going to be the 16. Okay, we do this in our head. 16 is the square root. So, no, it's the square root of 191. No, square root of 20. That's what it is. So the standard deviation divided by the square root of the sample size, which is 3 point, let's see how many places, 4 places, 3.5777. Oh, that's up here. 0.5777. Okay, what is the probability that a random sample of 20 pregnancies has a mean gestation period of 185 days or less? So it's the same question as this one up here, but now we're looking at just the sampling distribution. Well, we know the mean, we know the standard deviation, and we know, I have StatCrunch to do. The mean's the same. Standard deviation is now 3.5777. And I believe we just look at that. So in this case, it's going to be 0.0468. Much smaller than this one. Okay, interpret this probability. If 100 animals were put in this sampling distribution, we're looking at less than, I believe is what it said, yeah, less than 185 days. And if you time this by 100, you get 4.68. So in other words, five samples. Oh, I'm sorry. 100 independent random samples. Oh, yeah. There would just be 5. What is the probability that a random sample of 45 pregnancies has a mean gestation period of 185 days or less? So what we had back here was 20 pregnancies. Now here we have 45. So that's going to change our standard deviation. The mean's still going to be the same, but the standard deviation now is going to be 16 divided by the square root of 45. And we get 2.3, 4 places, so 2.3851. 2.3851. Oh, no, that's not where the mean goes. The mean just goes into StatCrunch. So 2.3851. Still the same question, less than 185 days. We compute that, and we get 0.0059. 0.0059. Again, asking 185 days or less, 2 spaces, that's going to be 1 sample. What might you conclude if a random sample of 45 pregnancies resulted in a mean gestation period of 185 days or less? This result would be unusual. So the sample likely came from a population whose mean gestation period is less than 191 days. Because 1 sample out of 100, that's a really rare probability, right? We found a probability of like 1%. It's actually less than 1%, but it rounded up to 1. So that's very unusual. Okay, what is the probability that a random sample of size 19 would have a mean gestation period within 8 days of the mean? So we have again a different sample size, 19 being the sample size. So our standard deviation change, or I should say a standard error, 16 divided by, in this case, 19 is the sample size, the square root. That is going to be 3.67, I'll go 4, so 3.6707. 3.6707. 3.6707. And here we're going to go between, because we know the mean is 191, and it wants within 8 days of the mean. Well, the mean gestation period within 8 days of the mean. So the question is it really, is it going to be 8, 191 minus 8 or 191 plus 8? Well, that would be 16 days. So I think it's reasonable to assume 4 on each side. So we're going to go 187 and 195. That's 8 days around the mean. We'll see if that's correct or not. 4 places passed, 7242. Okay, let's check that. All right, let's see if this one is going to be 8 days around there rather than just 4 days. So we'll go 191 minus 8. It's going to be 183. 199. 0.9707. 9707. Check that. And that's the correct one at once. So sometimes that can be confusing, but this is what they mean. If you see this question, within 8 days of the mean, that means 8 days on either side. I would have assumed it was the first one. That's why I did that one first, but it actually wants this one here. Okay, moving on. Okay, so this one says we have a simple random sample of n equal to 1,000. The population is, of course, 1 million. And here we have a population proportion. So we're not dealing with a sample distribution. We're dealing with a population distribution like this, population proportion specifically. And we have the population, whatever characteristic that we're looking at is 0.78. That's the proportion. All right, so describe the sampling distribution of p hat. P hat is the proportion distribution. Let's actually make sure my terminology is correct here. Sample proportion is what I should be saying there. The sampling distribution of a sample proportion versus what we were doing previously. So it's asking for describe the sampling distribution. And there are a couple things that we have to look at to make sure that it's approximately normal. Now, all of these are approximately normal, so we know it's going to be approximately normal. But the things we have to check are further on in this chapter. Look down here. We'll see that a simple random sample of size n with population proportion p is approximately normal, provided np 1 minus p is greater than or equal to 10. Now, there's actually another one that's not written here, which I don't know why it is. But if you go to the next page, you'll see that we want this. We want the sample size to be less than or equal to 0.05 of the population size. So 5% of the population, less than or equal to. That's to ensure independence, which it says right here, independent. So that's what we're looking at there. So there's actually two things you need to check. N less than, N being the sample size being less than 5%. Of course, 1 million, if you looked at 5% of that, 50,000. So this is definitely less than that. But also we need to look at n times p times 1 minus p. N is 1,000 times p is 0.78 times 1 minus p, or the difference between that and 1.00. So it's going to be 0.22. And that's definitely greater than 10. So we know it's approximately normal. Now we can go through and look at the mean and the standard error. Let me get back to the book here, go to the previous page, and that's where the formulas are for this. The mean is going to be the same as the population proportion. That's because it's always going to be the same. That's what you're guessing around it, so that's always going to be the same. The standard deviation, however, will change, and that's going to be p times 1 minus p over n, the square root of that. Okay, let's do that. The mean is going to be the same. That's why you see 0.78. But now we do p times 1 minus p, and then that's going to be divided by n, and then take the square root of this. So we get 0.13, and then it rounds up to 1, so 0.131. It's going to be b. Now that we have a standard, approximately normal distribution, we can use the normal distribution calculator to find the probabilities. And we're going to go standard. The mean is 0.78. Standard deviation is going to be 0.0131. And this is greater than 820. Or no, not 820. We want to find this as a proportion, not a number of characters. So to do that, we're going to take 820, and then of course our sampling size is 1,000, so we're going to divide it by 1,000. And that's the proportion we're looking at. And it says, what's the probability of obtaining 820 or more individuals? So it's going to be 0.82 or greater. Compute that. And we get 0.0, 4 places, 0.0011. Pretty small. Okay, 750. Let's bring up the calculator. 750. I don't know why I'm doing this. It's just moving decimal point 3 spaces. That one's pretty obvious. And less than or equal to 0.110. All right, let's check it. And it's all correct. Okay, this one looks to be very similar in that we're still working with the sampling distribution of a sample proportion. And we're going to just go through and answer some questions. So the first stop is describe it. And we got to figure out which one it is now. So we do need to test the things to see if it's approximately normal or not. So first off, we have, suppose a simple random sample of 600 adults is obtained. Now, how many population, or what's the population amount? Well, if it's 600 adults in a country, I mean, you can assume there's many people in the country, especially with their credit cards, so they can't be developing country. It's got to be a first world country probably. And so you'd assume there'd be way more than 600. So I think we can assume that these are independent. Now we can look at NP 1 minus P and see what we get there. Of course, it's 31%, so that's going to be the same thing as 0.31. So N is 600. N times P times 1 minus P, so 1 minus 0.31 is going to be 9 to 4, so 69.69. 128.34, and that is greater than or equal to 10, so we know it is approximately normal because N is less than or equal to 0.05 N and NP. Now what's the difference between this one? Oh yeah, greater than or equal to 10, so that's what you want. You don't want less than 10. It's going to be B. All right, the mean, well, that's going to be the same as the population proportion, so 0.31. Standard deviation, that was that formula we used previously. That's going to be P times 1 minus P divided by N, and then the square root of that. So we get 3 places instead of 4, 0.019. Always make sure you're checking these, what they say, because normally it's 4 places, but this one says 3 for some reason. So yeah, make sure you check those. Okay, what is the probability that a random sample of 600 adults, more than 34%, do not own a credit card? Okay, once again, we have an approximately normal distribution, so let's go ahead and use this calculator. We know the mean and standard error for this, so the mean is going to be 31. This is going to be 0.019. And it says more than 34%. So it's going to be greater than or equal to, and this is actually nice and easy because it's just going to be 0.34 instead of having that division like we did in the previous problem. All right, we have, okay, here it says round to 4 places is necessary. So 0.572. Okay, interpret it. 100 different random samples of 600 adults were obtained. We would expect, well, 600 times 0.0572, 34.32, so 34. To result in more, one would expect 34. Oh my gosh, what am I doing? 34 to result in more than, oh, I'm sorry. I need to read this. I was thinking 600, but it's 100 different random samples of, oh no, of 600 adults were obtained. Yeah. One would expect 34 to result in more than 34%. No, it's going to be 6. Because we're looking at if the 100 different random samples, of the 100 different random samples, each one of them having 600 adults, the probability is approximately 6%. That's what that says. So 6% of 100 is going to be 6, and that's going to be result in this number. So don't confuse as like I just did there. We're talking about 100 different samples. So you couldn't have a number over 100, for instance. You couldn't do 250, even though it's less than 600. It's not. It's more than 100, and that's what we're looking at here. Hopefully that makes sense. If it doesn't, email me. We'll talk about it. Okay, what is the probability that in a random sample of 600 adults between 29 and 34? Okay, so bring up StatCrunch again. So we're going between 29 and 34. 0.766. I think it was 7966. Yep. Okay, interpret this. So if 100 samples were taken, then we move the decimal point over twice. That rounds up to 80. 80 are expected to result. Okay, would it be unusual for a random sample of 600 adults to result in 174 or fewer who do not own a credit card? It would be unusual for a random sample to result in 174 or fewer. Why? Okay, so we have a single random sample of 174 or fewer do not own a credit card. So this whole thing is about, 31% of adults do not own a credit card. So what we can do first is find the population or the proportion for that random sample. So 174 divided by 600. This is the same thing as saying if 29% or fewer do not own a credit card. Well, we already have the distribution for that, right? It's this, and we're looking for fewer than 29%. So fewer than 29%, compute that, and we get 14.63. So it's not unusual. 5% is typically the breaking point between unusual or not. This is definitely greater than 5%, so it's not unusual. because the probability that p hat is less than or equal to the sample proportion is, yeah, it's less than or equal to the sample proportion. Just trying to figure out which one it is. Less than or equal to, which is greater than. So it's going to be this one. And the 0.1463, which is greater than 5%. So that's all we have. Let's check it. And it's all correct. Very good. And that's all there is to chapter 8. Well, I should say the chapter 8 review quiz.